We're going to start off, as I am wont, with a retrospective on yesterday. So yesterday we built three models of note. All three were distinguished by being hybrid system science models. And just to help people recall, one of them was an environmental contamination hybrid model, where we had different locations, and we had individuals who would go between homes and workplaces. The homes represented the residents, and multiple people would often live there. And then we had workplaces which were worked at by often many people, and individuals move back and forth between them, and exposures, for example, within a workplace, by inoculating an initial workplace, we could have some exposure occurring in the workplace, and people would bring it back home. It could spread at home in environmental pathogen reservoirs, and then spread from the home to different workplaces, and then to different homes in turn. And the way that this was realized is, while people were fairly routine in their depiction, we had susceptible shedding and recovered, and we had some alternation between work time and off time that would govern their travel. We had workplaces, and we had homes that each had a pathogen reservoir associated with them, and these pathogen reservoirs would start to secure pathogen as the model was running, as people shed into them, and in turn people would get infected with pathogen from these reservoirs, and that would lead people progressing to later to stages of shedding themselves, where they could shed it to other locations. So this model captured the fact that we have locations that can build up pathogen reservoirs, which then incorporate their own pathogen dynamics shaped by shedding, to be sure, but also by endogenous multiplication within the facility. And we could use different rates of pathogen multiplication within a facility or at a certain location, as might be governed by environmental conditions like humidity and temperature, to shape the evolution of these pathogen reservoirs at different locations. This model had rather coarse-grained representation of this, in the sense that we have pathogen reservoirs that were rather large in scope, say for an entire workplace or an entire home. But we could, of course, grid, harking back to the last model we looked at, we could grid up space and have the pathogen reservoir for each component of that space, and have people shed into one grid square or another, one patch or another, and have appropriate dynamics within those. So that was the first model we looked at, and that involved mobility. It involved hybrid in the sense that we had state charts and classic messages and networks within certain locations, or effective networks within certain locations, and then we had stocks and flows also governing things. So this showed one aspect of stocks and flows that seemed relevant to the veterinary context and the One Health context. Okay, so that was one model we built on, and that actually took the majority of time during the day. The last model just because I mentioned it, the last model we worked on was a little bit different. This model also incorporated space, so we had patches, and within any logic, the population of, so we had patch agents, there's a population of patch agents, and that population critically had a a number of agents defined as a count of patch rows times the count of patch columns. So it was a rectangle. So many columns, so many rows. And within main, if we look down in the space and network area here, we imposed a discrete space. And I noted that AnyLogic supports 3 types of spatial environments. Really, 2 of them are close variants, GIS and continuous. Both represent a continuous space, one with geographic meaning, latitude, longitude, the other with more abstract meaning, such as might be used for an indoor space or what have you. But then discrete, and big difference being that in discrete we have mutual exclusion. 2 individuals, so things in discrete space are blocked out into a grid, or what we call patches, and those patches are mutually exclusive and collectively exhaustive. We can only have 1 person or 0 people, or 1 agent or 0 agents of a given class in a given patch. So here with the discrete space, we delineate the number of columns and rows, and we specified a count of patch columns, a count of patch rows, in addition to the space width, sort of just the visual width of the space. And we set up a neighborhood type, saying that each cell is connected with its neighbors. I've actually provided you with a more sophisticated version of this, where we have neighbors connected toroidally. In other words, those at the top are connected with those at the bottom, those at the right with those at the left also. So it's an unbounded space that's depicted. Here we had edges, and those edges sometimes lead to strange effects in models. But this is how we set up our grid squares. We had this discrete network, count patch columns, count patch rows, as the number of columns and rows, and neighborhood type, and we said essentially a layout type of arranged. That will arrange things in a regular grid. You may remember that from the network lecture. And here patches, as I said, have this many patches. So they end up, or this many patches, so they end up being arranged in this grid. Okay? And so we arranged them in a grid, and each patch was governed. Could have had stocks and flows and state charts, but in this case, it just had state chart. There's just stocks and flows. And this stock and flow had a representation of endogenous behavior within a patch in the form of bursts, maturation, and deaths, but also some migration between patches. And we had a mortality rate and a birth rate. Now, while we were setting up, I decided I would change this model to make it a little bit more interesting. And if anyone's interested in following that, I moved birth rate into the patch, and I basically went to main, and I created a mean birth rate as a parameter for main and a standard deviation of birth rate, and then I actually had the patches here. Each patch now has its own birth rate as drawn from a normal distribution here, and I'll put this up on the big screen. So I had this imposed. So each patch now had its own birth rate as drawn from a normal distribution, truncated to be no smaller than 0. And what this leads to is a more interesting dynamic where you might have microenvironments which are really good for breeding. Think a coral reef surrounded by other environments, parts of a coral reef offering nice shelter sites for animals, compared to other regions which have less in the way of sheltering. And so now we have a situation where we have some variability over space in terms of the amount of growth you see and the fluctuations, and so you get some diffusion occurring. It's still not perfect. We could incorporate density-dependent growth where it's harder to give birth if it's a large population, but the idea was I introduced some extra variability. So this model captured dynamics of patches, and I noted that a model like this could be very useful for geographically situated patches. We could situate this in a GIS context so that each of the patches had a clear GIS location, and that would then govern the terrain type or availability of nesting sites, which might shape the birth rate and the migration rates. The migration rates here were done in a very simple way by diffusion through get net immigration rate, and we had some diffusion coefficient times a difference in the number of mature specimens in two neighboring patches. So we had sort of neighboring patches which could diffuse into a cell if they had more mature creatures than the cell at the center, or vice versa if the cell at the center had more than them. So another very useful type of modeling, and I gave you a model where we use this for West Nile virus, patches for West Nile. We've also used it for sea lice and for chronic wasting disease, where we have stock and flow dynamics of a given patch and then migration to nearby patches. Very useful. And as I say, you might want to look at the toroidal one. Okay, so this was a second type of modeling, and you could imagine this easily be combining with the first type by having those pathogen reservoirs that you might have in the first type of hybrid modeling incorporated in patches here, which are then laid out in space. So you'd have a grid of patches with different levels of pathogen reservoirs over which people would travel and shed, leading it to build up or decay in prion levels or in levels of antimicrobial resistant bacteria or what have you. Okay? The third type of modeling that we looked at was of a rather different sort yesterday, and that was what I called the lateral ABM hybrid modeling. And here, in contrast to the previous two types, while it is a hybrid model, we had a very different arrangement of system dynamics and agent-based. In all cases, they're system dynamics and agent-based. In those two cases, the first and the last, each agent had within it dynamics governed by system dynamics. So system dynamics was driving agent behavior, some or all of agent behavior. And there are system dynamics kind of within the agents. Here, by contrast, system dynamics is used in a way that's lateral to the agent-based modeling. So people start in a broader population characterized by system dynamics in a rough and ready aggregate fashion in a compartmental model. And we used a classic formulation of a mathematical epidemiology of an SIR model, SEIR model, or an SEI model here, to drive this. So we have an upstream population depicted in an aggregate way, and once people reached a certain point in the risk continuum, where they are marked as being part of a population of focal interest, a population where we're really interested in following their details, they turn into agents. And how does that happen? Well, they flow down to this stock, and this stock is kind of a temporary holding place, a clearinghouse for agents to be created. So people flow in here, and once this stock reaches a certain level, once it reaches at least one full person, we go through and we create that many people, that many integer count of people as agents. Okay, those agents are created as full-fledged persons, first-class persons. And by virtue of being created as a person, rather than being encapsulated in a high-level aggregate model, we can secure the normal benefits of individual-based modeling. And just to rattle off a few of them, we can follow that person as an individual, their history over time, which is not possible in general in an aggregate model. So we could ask how many times has this particular person been infected, try to track the relationship between that and their risk behavior, and potentially compare it to longitudinal databases. We could put them into networks that are explicit. We could situate them in space. We could further simulate the effects of articulated interventions that depend on any of those things, their spatial location, their network position, their history. We could further have them represent decision rules based on their situated context, where they have different preferences and make different decisions based on what they see around them, etc. So in short, there's many advantages to using individual-based models to answer certain types of questions. And questions which feature those needs, individual preferences and decision-making, needing to represent network structure, network dynamics, spatial behavior, individual history, and interventions depending on any of those are great candidates for where you'd use individual-based modeling. And we can get that. We can get the advantages here of individual-based modeling without having to make the entire model individual-based. We can have the upstream areas of the model, that 80%, that 90% of the population who are not all that centrally concerned about, are not at the forefront of our model. We can represent them in a very aggregate way, and only represent them at a detailed level when they are marked as being of particular interest or having a history of note, say they've been infected at least once previously, etc. So we get to simulate most of the population in a rough way. Kurt, maybe you could focus that a bit. And the population we care about in a very detailed way. Thanks. Ooh, that's better. In a very detailed way. So this was a different sort of modeling, and just to give you a sense of how that runs, we could run this like this, and you'll notice this is building up. It's getting up to the point where we'll get one person created, okay, and now more people are being created as they reach that point within the model. So conceptually what's happening is people are flowing to a certain point and then becoming agents. They're being individuated as agents. Now, we didn't spend any time modeling the agents in any details. In some models we've built, say of a hospital or of a care facility, these people at some point actually flow back into the stock and flow model. They no longer are focal interest. They've been delivered the care they need, and they actually become, they go back into the stock and flow model. So there's actually a round trip to stock and flow. You get great economy of expression for most of the population, very lightweight modeling. You don't have to go into all the details for most of the population, and yet you save your energy for those details for the population you really care about, those population of individuals of focal interest. So this is the third type of hybrid modeling we saw, also of considerable interest in a veterinary context. Okay? Any questions about these models from yesterday? Yeah?
How would you get like JS layer on your patch model? Like how would you do that? As you have got a discrete space.
Yes, yes.
So how do you get
okay, that's a very good question. So, so AnyLogic's GIS features are available in, so if we go to here, the types of and space and networks, they're traditionally used in the GIS mode here. And if we were to, I won't do it for this model, but if I were to go create a new model, here what you'd find is that when you switch into GIS mode, suddenly, this is a new model, suddenly things happening. So you start getting this map imposed, and there's a bunch of mechanism that's now available because of that. So I would pursue it in one of three ways, okay? The first thing I would do is I would actually try to see, I could do a similar spatial layout of patches in this context, laying them out. What I'd have to do is, it wouldn't depend on it to automatically arrange them in a grid. I would instead place them in a grid at defined latitudes and longitudes by iterating through a certain region. And that should be readily done. I would have a patch. I would have a patch agent, and that much would be the same, the patch agent. What would be different is that patch would be told, rather than being automatically placed in this grid by this space network thing here, I would actually make latitude and longitude of a person something that is set in a bit of startup code that would say place the person here, 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 here in a grid-like fashion. And Kurt or I over lunch could probably write that up, the code to do that. It's a straightforward thing. So that would be one of the strategies I'd use. A second strategy is one that we've actually used successfully, and I'm having trouble remember all the details of it, but it actually involves a model where you can use both discrete and continuous grids, so discrete grids in continuous space in the same model, and by extension GIS space. And I'm trying to recall the exact details of it, but I believe I could share a model with you. I believe I've got it on this computer that I could share, which illustrates some features of that. So there we actually juxtapose a gridded model and a continuous model. And one way to do that is to have main and then have a GIS sort of accessory to main embedded within main that covers that same area. So main is a discrete space and the other one is in patches. And I think that would also work fine as a technique. And as a third technique, this would have to be verified, but maybe it's something for Krugerian investigation. But my guess would be that you could use AnyLogic's GIS calls outside of this GIS space type. In other words, I think those calls you should probably be able to tap into manually by calling them explicitly outside of the need for this. And you could probably make a model work just fine. Even though it's a discrete space, you could probably manually call the GIS features to treat it as a geographically mapped model. Those would be three ways, and Kurt or I could probably prototype something for you before the sun sets that would show these features.
If you've got a model already, that would be.
Yeah, so I do have a foodborne illness model, which if people are interested, I could show. But it's a model which also was built in a somewhat different version of AnyLogic, so I'd have to make sure it works just fine in this version. Okay, any other questions about models from yesterday? Three types of hybrid models. Now, you will find in your slides folder, there's a folder called Hands-on Hybrid Modeling, and that overviews a set of different hybrid models that I found really helpful. And yesterday and in previous days, we hit 4 out of them, I think. This one, service population interaction. This is where people presented for care at a discrete event model and were treated by that. We saw that in day 2. This individuated at-risk population and broader aggregate population. That was that budding model we saw yesterday, the middle model. System dynamics driven agent evolution. We saw that in the first and in fact the latter model. These two actually we haven't actually explored much. I have a model that I provided to you that's a health economics model where we have aggregate system dynamics, and I'm just going to go call that up in case you would find that of interest. This is available in your online models that I've provided, and it is called Basic Health Economics. Okay, some of you in the original surveys had expressed interest in capturing health economic effects, and I'd like to highlight this one for you as another hybrid model. So here we have a pretty vanilla agent representation. And this agent representation of diabetes and end-stage renal disease includes certain factors aimed at health economics in nature. So there's an activity-based costing model where there's states you can be in and then some cost per year of being in a certain state. Okay? And then also each state has a quality of life, a health-related quality of life indicator, as might be elicited through some health utility scale, health utility instrument. Now, more than that, there are also certain episodic costs, events that costing. So in addition to certain costs just being in a given state, there are also costs associated with acute events, things like a transplant that someone receives, that also accumulate costs. And all of these types of costs, ladies and gentlemen, are then accumulated in health economic terms in measures that are aggregate across the population. Accumulated undiscounted costs, accumulated discounted costs, and then life years lived in quality adjusted life years lived here. So this will total up the quality adjusted life years and the life years lived across the population, and it does so by system dynamics. So for life years lived, all we're doing is we're totaling up over continuous time. Therefore, we're integrating up the population size. So if we have one person, they live for 10 years, or 10 people and they live for 1 year, the net result is 10 life years accumulated. And that's exactly what this does. It's a very beautiful declarative way of specifying some of the basics of health economics. Life years lived, this is a flow into it whose size is defined by the size of the population. That's just this population, our agent population size. For qualities, by contrast, we're going to total up a statistic defined in this population, which is going to take the average of quality of life over that population. And if we go here, we will find new costs per year, cumulative qualities. Here it is. A sum up over the population of people's quality of life, and that becomes this flow in that is going to flow in for qualities. So we sum up the population, counting people, not each person as one, but counting them according to their quality of life. So if someone's quality of life is 0.7 and others is 0.3, collectively they sum up to 1, and you keep on summing up, and then that flows into qualities. And there's a similar thing for costs, for undiscounted, and then there's a discounting factor. Per standard practice, there's a discount factor which is applied, which ends up influencing according to a discount rate for discounted costs. And you can have similar discounted qualities. So this model is described online. It does take into account as well, although I'm not going to have time to go into it in detail, the effects of intervention costs. So if you're intervening upon this population to lower the burden of diabetes, there's some intervention-related costs for lifestyle interventions, which are on a per-person basis, per person intervened upon, and it totals that up across the number of people receiving the intervention. So this is an example, ladies and gentlemen, of this sort of model where agent behavior, the behavior of these particular agents, ends up affecting aggregate dynamics that are captured by stocks and by flows. Okay? So this is agents drive aggregate system dynamics model. And then finally, I don't have a good example to show at the moment, but here system dynamics captures at the higher level things like environmental and policy dynamics, and that affects in turn the agents. So there's some dynamics in the environment that affects agents. And you could almost think of that first one we made yesterday, where we have persons and workplaces, as being a little bit like this, in the sense that we have workplace dynamics which are occurring at the workplace, and individuals are exposed to them and proceed through their state charts accordingly. They proceed through their natural history of infection due to exposure to these more coarse-grained, like per workplace pathogen reservoirs. Okay? Now, another thing that I wanted to make sure you're aware of, in some boot camps focused on chronic disease, I've emphasized it a lot, and I'd be glad to put together an example if there was interest. It's just opportunity cost and triage is foremost in my mind today. Are models where we have interacting state charts. And once again, in your set of example models that I've provided you, I've provided some examples of interacting state charts, which involve some outcomes in terms of one state chart affecting the other. And I provided you with a model called interaction of weight and diabetes. And this is something we alluded to yesterday, but here we have weight and diabetes state charts. And the key thing, folks, is that your weight status affects your hazard rate of developing diabetes. Okay? And here we have interaction of diabetes in weight, it's called, and then you have a rate here of developing diabetes that depends on this variable, this interaction of diabetes in weight, which is up here. So this variable captures the effects of different levels of weight on your hazard. And as you go up in weight, you have initially a lower rate of diabetes, and then you have successively higher rates of risk, a hazard rate of developing diabetes. And there's a beta term that's multiplied by this to give some hazard rate of going from here to here. So the key idea here is that this state chart influences this one via a variable. Just like we've seen it before. Remember when we wanted to set a color be different, when you were in different states, we would set a color. Remember that? Color equals green, color equals red, color equals gray. Remember that? So it is here. We just have, as it were, conceptually a hazard rate for diabetes that's set depending on which state you're in here. And then that is going to apply over here. Okay? The one trick with this is that there are exceptions, and in fact, if you're depending on transitions between states in another state chart, it's one of them. But to do this, apply this in general, like for changing age, you want a self-transition that will periodically go out and come back in and wake up to a changed hazard rate. If that hazard is being changed by change of another state chart, it's my strong recollection that this is not needed. But if your hazard rate here is dependent on something that's changing, like your age, then you do need something here so it wakes up and realizes, oh, I'm older, what's my new hazard rate to go from this to this. So interacting state charts are a very important feature of some models, and you should be aware that variables provide a formidable way of accomplishing this, but that sometimes you need these self-transitions to do that. Where did we see that self-transition yesterday? Does anyone remember? Where did we see a self-transition? It's right here. For the risk of environmental exposure, because your risk of exposure might change over time, you periodically, once every hour I think it was, you'd sort of check what's my current risk, and it would recompute this hazard rate according to my current pathogen exposure. And that reflects the fact that maybe I changed from home to work, or vice versa, or maybe the fact that the workplace is building up pathogen whilst I'm there. Okay? Okay. Are you getting close to cracking? Okay. So that was our retrospective on yesterday. Any questions on this?
So, Nick, would you like him to check to see if the foodborne illness model does work?
Pardon?
Would you like him to check to see if the foodborne illness model does work?
Oh yeah, that'd be great.
Okay. What I'd like to do is, just because we're all going and finding the right version of that, could I do it over a break? Is that okay?
Nope.
Just
Anytime today.
Yeah, great. Okay, we'll do that. And it's an interesting model. I might be able to find a good presentation on it where I could actually systematically lay out why we're building this, the type of research questions we're trying to answer, and how it relates to some data we're collecting right now on a longitudinal study with smartphones, using sensor data combined with survey data, where people are recording their exposure to foods of different sorts and are tracking when they're feeling ill and are tracking when they're when they are eating, and we're tracking over time their, both through proactive self-report and in response to questions, their food consumption and exposures, and attitudes and beliefs, knowledge, attitudes, and beliefs involving food. Okay, so ladies and gentlemen, that was yesterday. Today is today. Okay, so we're going to close that out.